So first we'll read the question for x4 or for 6.4, exercise 6.4, and then we'll talk about what it really means, what it's really asking you. So it says, for each of the following reactions, predict the sign of delta G. If a prediction is not possible because the sign of delta G will be temperature dependent, describe what delta G will be at a high temperature. Describe how delta G will be affected by raising the temperature. So first of all, delta G tells you whether a reaction is likely to happen or not. If delta G is negative, that was by convention, that's a negative delta G indicates that you have a spontaneous reaction. That means that the reaction is likely to happen. A positive delta G means that you have a non-spontaneous reaction. That reaction is not likely to happen. So when they say predict the sign of delta G, what they're really asking you is, are each of these reactions likely to happen or not? Now, when you try to figure out whether a reaction is likely to happen, you want to think of it in terms of, you want to frame the question in terms of the Gibbs free energy equation that you learned in general chemistry too. We know if delta G is negative, the reaction is likely to happen, and if it's positive, it'll be unlikely to happen. But what does delta G depend on? It depends on the arrangement of energy in space. So is the energy arranged in a way that's probable? So that's the enthalpy, which is really just the heat. Enthalpy is heat at a constant pressure, so it's basically the heat, unless the pressure is changing in the room that you're doing your reaction in. So delta H minus T delta S, the second thing it really depends on is the arrangement of the molecules. So here you're asking, is a reaction likely to happen? And if it is, then you'll have a negative delta G. And the equal sign is basically just saying it depends. What does it depend on? First, it depends on the arrangement of the energy. Is the energy likely to change this way? And second, it depends on the arrangement of the molecules. Oops. Are the molecules likely to change this way? And so, remember, if you're trying to think about these changes, and you're trying to think about whether something is likely or not, remember the principle that stuff spreads out. If you had 4 quarters, a black quarter, a green quarter, a blue quarter, and a red quarter, how many ways can you get all heads? There's only one way. Every single one of the quarters has to be heads. But how many ways can you get one tails and the rest heads? There are 4 ways. You could have the black one be tails and the rest heads. You could have the green one be tails and the rest heads. You could have the blue one be tails and the rest heads. Or you could have the red one be tails and the rest heads. So there are 4 ways that you can get that one tails and the rest heads. Similarly, if you were to have 2 containers, and if you have 4 gas molecules, a black one, a green one, a blue one, and a red one, how many ways can all 4 of these stay on one side of the container? There's only one way. All 4 of them have to stay on the one side of the container. But how many ways can you have one go to the other side of the container? There are 4 ways. The blue one can go, the red one can go, the green one can go, or the black one can go. So there are 4 different ways. So which one is more likely? It's more likely that one of the molecules will spread out, that it'll go to the other side of the container. because there's only one way that they can all stay on one side, but there are 4 different ways that they can go to the other side. There are 4 different ways that they can spread out. Now that's true if you have 4 molecules, you have 4 different ways, but imagine you have a mole of molecules. You could fit a mole of carbon atoms in the palm of your hand. If you had a mole of gas molecules, there would still only be one way for them to all stay in one place, but there would be 6.022 times 10 to the 23rd ways that one molecule can move to the other side. And so it's so much more likely that it'll go to the other side that is what happens every single time. Stuff spreads out. And we have it in this glass container, but imagine you take the container away, the same principle holds. There's only one way these atoms can stay together. There are many, many ways that they can spread out into different directions. And so stuff always ends up spreading out. And that's the principle behind diffusion. So if you put dye in a glass of water without stirring it, the dye will eventually spread out through the whole container. And diffusion is what moves everything throughout a cell. And it explains a whole bunch of things in life in the world that I may make a separate video on to go through. But for right now, the principle you want to remember is that stuff spreads out. Stuff spreads out. When stuff is spread out, it's always more likely that the spread out arrangement will happen, just in terms of sheer probability. So if we go back to this equation, and you're thinking, is a reaction likely to happen? Well, is the energy likely to be arranged in this way? In other words, is the energy spread out? If you have let me copy this equation. If you have an exothermic reaction, then the energy is spreading out. It's starting in one place and it's being released into the surroundings. It's spreading out. So that's likely to happen. And you'll notice when a reaction is exothermic, delta H is negative. And that helps to make delta G negative. In other words, it makes the reaction likely to happen. Now, the signs for delta S are a little tricky because you have this negative sign in the equation. So if delta S, if the entropy increases, and we had a previous video where we talked about that, if the molecules spread out, either by forming more molecules or by forming straight chains rather than rings, if they spread out, then delta S is positive because you subtract that term, the whole term is negative, and you could see that when the molecules spread out, it helps to make the reaction more likely. So if you have an exothermic reaction where the entropy increases, that reaction will always happen. On the other hand, if you have an endothermic reaction, delta H is positive, there you're taking energy that's already spread out and you're smushing it into a small space. The molecules are absorbing it and using that energy to make bonds. Well, that's unlikely. That's not very likely to happen. Because stuff was spread out, it can exist more ways that way, and you're forcing it in a small space. And you'll notice that would contribute to making delta G positive. In other words, non-spontaneous, unlikely to happen. If the entropy decreased, so you go from more molecules to fewer molecules, or a straight chain to a ring, and delta S is negative, you subtract that term. When you subtract a negative, you get a positive, and you can see that reaction will never happen. An endothermic reaction where the molecules come together will never happen. It's completely unlikely. Delta G will be positive all the time. So there are 2 cases where the temperature doesn't matter. Notice that's the one thing we haven't talked about here. That there are 2 cases where the temperature doesn't matter. The reaction will always be spontaneous, or it'll always be non-spontaneous. But sometimes the temperature does matter, and that's when the heat arrangement and the arrangement of the molecules disagree. For example, you could have a likely arrangement of energy, but an unlikely arrangement of molecules, and so they are pushing delta G to be opposite signs, and what wins ultimately is the temperature. The temperature is being multiplied by the entropy. It determines how influential this entropy is. And so it determines which variable wins. So for example, if you had an exothermic reaction, so the energy is going to be arranged in a way that's more likely, but the molecules are coming together, so they're being less likely. So when you subtract those, you get a positive sign. Everything depends on the temperature. If the temperature is big, then this term will be big, and delta G will be positive. If the temperature is small, that term will be small, and this won't make a difference, and delta G will take on the sign of delta H. So you could see how the temperature will be the deciding factor when the enthalpy and the entropy disagree with each other. So let's use those ideas to just think about these equations. We're going to write that equation down for each of these, and then we're going to plug in a sign for delta H and delta S to try to figure out the sign of delta G. And ultimately what we're doing here is trying to figure out whether a reaction is likely to happen by thinking about the probability of the arrangement of heat or energy and the probability of the arrangement of the molecules. So we know a reaction is likely to happen. It depends when you're assessing that, it depends on the arrangement of the heat and the arrangement of the molecules. Now we know they're giving us that it is an endothermic reaction. That means that the heat is changing in a way that's unlikely. It's starting out spread out, and it's being absorbed and condensed into the molecules, crystallized as bonds in the molecules. So that's unlikely. But this shows an increase in entropy. That means that the molecules are spreading out. That is likely. When you subtract that term, when you subtract a positive, you get a negative. So you have two competing signs here. You have the positive sign from the heat and the negative sign from the whole entropy term. So which one wins? What's the sign of delta G? Well, here they said if it depends on temperature, if delta G is temperature dependent, describe delta G at a high temperature, if you raise the temperature. Well, if you raise the temperature at a high temperature, you multiply that by the delta S, and this whole term becomes ginormous. So you end up with this huge negative term. And that ends up outweighing the positive sign on the delta H, and delta G is negative. So if the temperature is gigantic, you multiply the entropy by it, and now the entropy term is the big term, and it overshadows the enthalpy. So delta H is negative, and at a high temperature, that reaction is likely to happen. In other words, delta G would be negative. If we're looking at B, we're going to think through this in the same process. Is the reaction likely to happen? It depends. Is the arrangement of heat likely? And is the arrangement of the molecules likely? Well, they're telling us that it's an exothermic reaction. That means heat is spreading out. That's likely. Delta H is negative. They're also telling us that the entropy increases. So the molecules also are spreading out, and that's also likely. If you subtract that positive term, you get a negative. So it doesn't matter what the temperature is here. Both the enthalpy and the entropy are negative, and so delta G will be negative. This reaction will always happen. Delta G is negative. That reaction is always likely to happen. Okay, next scenario. Is the reaction likely to happen? It depends. Is the arrangement of energy likely? And is the arrangement of the molecules likely? They give us an endothermic reaction. That means heat that is already spread out is coming together. Well, it's not very likely that that's going to happen. That's a positive sign for delta H. And they tell us that we have a decrease in entropy. So the molecules that are spread out are coming together. You're either getting fewer molecules in your product, or you're getting straight chains turning into rings. Well, if you subtract that negative sign, that ends up as a positive, and delta G, doesn't matter what the temperature is, delta G will always be positive in this scenario. This reaction is unlikely to ever happen. Finally, same process of thinking. We have, is a reaction likely to happen? That's what delta G is telling us. It depends. It depends on whether the arrangement of heat is likely, and it depends on whether the arrangement of the molecules is likely. So here they're telling us that it's an exothermic reaction. Heat starts in one place and it spreads out to the surroundings. So that's the sign for that is negative. That's likely to happen. But here we have a decrease in entropy. So the molecules are coming together. Either more molecules are coming together to form fewer molecules, or straight chains are coming together to form rings. So decrease in entropy. Now if you subtract that term, that gives you a positive sign, and you can see that when we're trying to predict the sign of delta G, the delta S terms and the delta H terms disagree. So everything here will depend on temperature. They told us in the problem, if it depends on temperature, describe how delta G will be affected by raising the temperature. Now, at a big temperature, this term becomes really, really big. The temperature is being multiplied by delta S. So if you multiply a big number by delta S, that becomes a really positive term. It was normally positive before, but if you raise the temperature, it becomes really positive, and that overshadows the enthalpy. And delta G takes on the sign of delta S because it's bigger at a higher temperature. And so that at a high temperature, that reaction is not likely to happen. Delta G would be positive. If you want that reaction to happen, you need to make the temperature really, really small. You need to put that reaction in an ice bath. So this is just a way of thinking critically about chance, right? All we have here is chance. We're not assuming determinism. We're not assuming we can predict things. We're just saying if everything happens by chance, what's likely to happen? And what's likely to happen is that stuff spreads out. There are more ways that stuff can exist spread out than it can exist all together. And so this equation just divides that into thinking, is energy spread out and are molecules spread out? And based on that, you can figure out whether the reaction is likely to happen. If it's likely to happen, delta G will be negative, and if it's unlikely to happen, delta G will be positive. So you can think through each of these terms. You can think through that equation to organize your thinking and figure out whether you can use the temperature to favor products or reactants.